In our research, we present a shape optimization framework for product customization with standardized components. To begin, let's define the problem we are going to handle. For an example, we are given a bicycle as the product. It is composed of a set of components. Some of them are flexible, such as belt and adjusters, so that they can be adjusted or customized. Some of them are unchangeable, such as pedals, seat saddle and gears, so that they are required to be rigid. Some of them are standardized components, such as wheels, handlebar and frame, and each of them are accompanied with an element library. Therefore, the problem now is how to formulate the shape optimization, such that the customization consider the rigid and standardized components. We develop a mixed integer as rigid as possible, MIARAP, shape optimization framework. The shape optimization is formulated as an as rigid as possible deformation problem that is computed on volumetric meshes. The components are fixed to a predefined shape by a rounding operation. The yellow tetrahedra are the standardized component, and the orange tetrahedra are the predefined shape of it. After rounding, the shape of it is enforced to the predefined shape by hard constraints. The functionality of the framework is demonstrated by 3 experiments. First, a standardized component is embedded in the domain. This is to test if the optimization can converge. The domain is scaled down in y direction to be the target domain. The component is deformed together with the domain, and it should be returned to its original shape. After scaling down, another example is the template scaling up in y direction. Not only for scaling, some free-form deformation is applied for demonstration. Here, the target domain is blended. In the second experiment, we do a similar test as the previous one, but this time we use multiple standardized components, and the components are put close to each other. We aim at showing the behavior of the optimization and interaction between multiple components. A blending deformation is applied as the target domain. Then, a sharing deformation is applied as the target domain. We can see that although the components are very close to each other, but the optimization still can give a bijective mapping between them. This experiment shows that our framework has no difficulties to handle multiple components. For the previous examples, only rigid components are considered. But when an element library is given, the framework should be clever enough to choose the best match shape. Therefore, an iterative rounding approach is developed. In the third experiment, 4 element libraries are given. They are the element libraries of cube, bolt, nut, and I-beam. In this experiment, The components are embedded in a rectangular template domain. The template domain is then scaled down in Y direction to get the target domain as an illustration. For the first step, as there is only one shape in the element library of I-beam, that is, I-beam is rigid, and no selection is needed. Therefore, it is rounded first for the priority phase. The iterative round approaches starting by comparing the current shape of the components to the shapes in element libraries. The most similar one is selected out. Similarity is based on as rigid as possible energy, and the smaller the best. Among all pairs, the one with the smallest energy is rounded. Nut is rounded in this step. After that, the similarity is recomputed for the components which are not rounded yet. This time, cube is having the smallest energy, and it is rounded. Finally, bolt is also rounded to its best matching shape. Once all components are rounded to priority phase, they are further rounded to the projection phase, which is converting them into position constraints. Again, the smallest energy is rounded first. To conclude, for scaling down, C3 is selected for cube, M4 is selected for bolt, and M4 is selected for nut. One more example is done by shearing. This time, C4 is selected for cube, M5 is selected for bolt, and M5 is selected for nut. Go back to the bicycle example mentioned before. Recall that wheels, handlebar and frame are the standardized components, and they have their element libraries. The shape optimization is driven by human skeletons. For different postures and bodily forms, the bicycle is customized accordingly. Sometimes, even the combinations are the same, positioning and configuration for the bicycle are customized specifically. This framework is very useful for some electronic or mechanical products. The electronic and mechanical components cannot be varied. Simply wrapping the products to fit another body will deform them as well. With the help of our framework, the customization of such product can be realized. Circuit board is an essential part for electronic products. Although the shape of the circuit board can be customized, CPU, RAM sockets cannot be customized. Our framework can produce the customized results while keeping the components in standard shapes. More importantly, our method can ensure the mapping is bijective. It means that the conductive traces will not merge or intersect with each other. As a result, the customized PCB can be directly manufactured, and the components can be soldered on the circuit board without any difficulties. This is the end of the video. Thank you for watching.